Welcome to The Explainer. You ever stop and wonder how your computer can stream a 4K movie, download a massive game, and let you scroll through 100 open tabs all at the same time without just grinding to a halt? I mean, it really does feel like magic. But today we're going to unpack that magic. We're going to see how computers are built to juggle everything at once.
So what's the real secret sauce here? When you think about a powerful computer, your mind probably jumps straight to more processors, more cores, right? And look, that's definitely part of the equation, but it is not the whole story. The real key to the performance we take for granted today is way more interesting, and it's all about solving a fundamental traffic problem happening deep inside your machine.
All right, so let's start at the beginning with the evolution of the computer's brain, the processor itself. This is really a story about going from a single overworked manager to a super efficient, coordinated team.
Back in the day, computers pretty much all had a single processor system. That means there was one main CPU, one central processing unit that did all the heavy lifting. We're talking running your programs, crunching the numbers, basically everything. Sure, you had other little specialized chips, but there was only one general-purpose brain making all the big decisions.
Then came the first huge leap forward, the multiprocessor system. And yeah, it's pretty much what it sounds like, a computer with 2 or 4 or 8 or even more processors all working together. But here's the crucial part. They're in close communication, sharing things like memory. They're not just roommates living in the same box, they're a tightly knit team. That's why you'll also hear them called parallel systems.
So why do this? Well, the benefits are huge. First, you get a massive increase in throughput. More workers means more work gets done faster. Simple as that. It's also just a better deal. It's way cheaper to share one power supply and motherboard than have a bunch of totally separate computers. And maybe most importantly, you get a boost in reliability. If one processor has a bad day and fails, the others can just pick up the slack, keeping the whole system from crashing.
Now, there are two main ways to organize this team of processors. On one side, you have symmetric multiprocessing. Think of this as a team of equals, a special ops crew where every member can do any job. Any processor can run any task. Then you have asymmetric multiprocessing. This is more like a traditional manager and employee setup. You have one master processor that acts like a manager, assigning specific jobs to the other slave processors. Both work, they're just different management styles for the computer's internal team. Okay, so we've beefed up the computer's brains. Awesome. But even the most powerful brain is totally useless if it can't talk to the outside world, right? If it can't interact with its senses, like your keyboard, your mouse, or your hard drive. And that brings us to the second, and arguably more complex, half of our story, the input-output challenge. So, every single thing you plug into your computer, your mouse, your monitor, your external drive, has its own special piece of hardware called a device controller. You can think of it as a dedicated port manager, or maybe the bouncer at the door for that specific device. It's the physical middleman, and it even has its own little patch of temporary storage, called a local buffer, to hold data coming in or going out.
Now, if the controller is the hardware, the driver is the software that tells it what to do. The driver is like a universal translator for your operating system. The OS doesn't need to know the nitty-gritty details of every single hard drive or mouse on the planet. No way. It just talks to the driver, and the driver translates those commands for that specific controller. It's an absolutely brilliant system that makes everything plug and play. So, we have powerful processors and we have a way to talk to all our devices. But this creates a brand new problem, a massive potential traffic jam. How do you move huge chunks of data, like a video file, from a hard drive into memory without constantly bugging the main CPU to do all the work? This, my friends, is the story of the slow road versus the superhighway.
The old way, the slow road, was called interrupt-driven I/O. To understand this, just imagine the CPU is the CEO of a huge company. With this method, every time a single byte of data, think of it as one letter, arrives at the device controller, the CEO has to stop everything they're doing, get up, walk over, pick up that single letter, and personally carry it over to the main filing cabinet, which is our main memory. Now imagine doing that for a file with millions of bytes. It's insane.
And, as this quote from our source material points out, this whole process created a massive bottleneck. That high overhead it mentions, that just means the CPU, our CPU, is spending almost all of its valuable time just being a delivery person instead of actually, running the company and executing your programs. It works okay for tiny things like a single keystroke, but for a big file, forget about it.
The solution, the superhighway, is a beautiful piece of engineering called direct memory access, or DMA. DMA is a total game changer. It basically empowers the device controller, let's call it the mailroom clerk, to take the entire mailbag, the whole block of data, and move it directly into main memory all by itself without involving the CPU at all. The CEO is only bothered twice, once at the beginning to say, hey, start the transfer, and once at the very end to get a memo that says, all done.
And the difference here is just night and day. Instead of one CPU interruption for every single byte of data, DMA gives us just one interruption for the entire block of data. This is the whole secret. DMA frees up the CPU to go do other important things, like keeping your video call running smoothly while that giant file transfer happens quietly in the background. This is why your computer doesn't freeze anymore when you're saving a big project.
So let's bring it all home. We've seen how computers got more brains through multiprocessing, and then how they developed a much smarter workflow for handling data with DMA. These two innovations, working together, are really the twin pillars holding up all of modern computer performance.
And that really gets us to the core idea of this whole explainer. True, modern performance isn't just about raw speed or having more processor cores. It's about the entire system working together in harmony. You need both a powerful architecture, that team of processors, and an efficient data management system, that DMA superhighway that lets them do their jobs without getting stuck in traffic.
So we figured out a brilliant way to get around the CPU bottleneck when moving massive amounts of data, and that unlocks the incredible performance we all enjoy today. But, the quest for more speed never ever stops. Which leaves us with a really fascinating question to think about. What's the next great bottleneck in computer engineering that we're going to have to solve? Thanks for watching.